So we've already talked about the distance between 2 points, and what this video is going to do is extend that definition of distance to the distance between points and lines, as well as the distance between parallel lines. And the reason we need to talk about this is because it's relatively straightforward to talk about the distance between 2 points, which we've defined and we've seen as the length of the segment that connects those points. So the distance between our 2 points that we have in the diagram at the top right is the length of this segment. Now we could also draw any other sort of curve that we wanted to that goes from point to point, and that curve would be longer than the segment. And the reason that we define the distance between 2 points to be the length of the segment that connects them is because that line segment is the shortest distance. Well, talking about the line segments that connect a point and a line becomes a little bit more complicated, because no matter the length of the line, even if it's a point to a line segment, we still have an infinite number of segments that we can draw from that point to that line. And so just saying it's the length of a segment from the point to the line doesn't actually tell us anything. And this line, if it extends forever, could have this segment that meets it many, many, many inches, or even many, many, many miles if they are nearly parallel but not quite, over off to the right-hand direction. So we need to have a different way of talking about distance between a point and a line. And so much like we choose the shortest length, which is the length of a segment between 2 points, we choose the shortest distance between a point and a line, or the length of the shortest segment that we have between a point and a line, so that we can talk about the distance, because we use the word the, meaning the one and only distance between a point and a line. And the shortest segment between a point and a line is perpendicular to the line. So the distance from a point to a line is the length of the perpendicular segment from the point to the line, drawn in red here. Go ahead, pause the video, copy down this definition as well as the diagram, come back when you're ready to move on. So this is a relatively straightforward definition. It's relatively easy to find the length of segments here if we can show it's congruent to another segment, if we have a way of measuring it. There are many, many different ways that we could find this, and this definition is relatively straightforward. Before we get into talking about the distance from one line to a line that's parallel to it, we have to talk about an important fact about parallel lines. And that is, if 2 lines are parallel, then all points on one line are equidistant from the other line. What that means is that if you choose an arbitrary point on the top line and find the distance from that point to the bottom parallel line, it should be the same distance for every point along the lines, no matter which one we choose. Now, since these lines are parallel, you may be able to intuit, well, of course, those vertical segments look like they are all the same length. And when we have horizontal and vertical parallel lines, it's relatively easy to see that. But not all lines are necessarily horizontal or vertical, and if we're on a coordinate plane, for example, like you spend a lot of time in algebra doing, and we want to find the distance between 2 lines that are in fact diagonal, then we need to rely on something like this theorem here, that if 2 lines are parallel, all points on one line are equidistant from the other line. So the way that we're going to prove that here in the video is we're going to shorten those 2 lines so that we have a space to write our proof, and we're going to choose 2 arbitrary points on our top parallel line here, A and D, and we're going to drop perpendicular segments to line BC. So the segment AB is the distance from A to BC. The segment DC is the distance from D to BC. And because these are arbitrary segments here, they're not points chosen in any particular orientation other than they're not the same point. If AB and DC are congruent, that means that the lines are equidistant no matter the points. So this is what we want to prove. AB is congruent to DC. So as we're setting up our proof, the first natural question is, what are our givens? Well, the first given is that AD is parallel to BC. That has to be true. That's our if 2 lines are parallel. And then we also know that AB is perpendicular to BC and that DC is also perpendicular to BC. These are constructed, but that is part of the given. We're looking for all points on one line to be equidistant from another, so we have to draw the segments that allow us to calculate distance. Now, before we go on, go ahead and take a look at this and see if you can find any ways that you might go about proving this. We're going to go in one particular way about this proof, but there are many ways. So take a few seconds, pause the video, see if you can determine one way or maybe many ways that we might go about this proof. Come back when you're ready to see the proof. So as a part of all of this, you're going to be asked to write down the if-then statement. If two lines are parallel, then all points on one line are equidistant from the other line, as well as the diagram and the proof. So you can pause the video and do that now, or you can wait to the end of the video and write down the whole thing. But let's go ahead and get started. So what we're given is all of the information we already talked about. We have two parallel lines, which is very nice, because parallel lines tell us something about transversals. Well, as it turns out, line BC is also a transversal for segments AB and DC. And we notice that angle ABC and angle DCB are both right angles. And they're also same side interior angles if BC is a transversal for AB and DC. And because they're both 90 degrees, 90 plus 90 is 180, those angles are supplementary. And so we know that AB and DC are parallel because of same side interior angles theorem. Great. That is now incredibly helpful, because now that we have sets of parallel lines, we can talk about angles like alternate interior angles, same side interior angles, all of those different things. And so what we're going to do is we're going to draw a transversal from B to D. We don't have to say that we're constructing that. We can just add it to the diagram, and there it is. Now let's start looking for some congruent angles and some congruent segments. Again, there are many different ways you might go about this, and there are other congruent angles that you can choose here. But the one congruent segment that we see, to be sure, is that BD is congruent to BD by the reflexive property. Or because it's a shared side. And using BD as a transversal, we also have other sets of congruent angles. Angle ABD and angle BDC should be congruent there, as well as angle ADB and angle DBC. Angle DBC. And those are alternate interior angles, so we can use the alternate interior angle theorem. Well, now we have two angles of one triangle, as well as their included side, be congruent to two angles of another triangle, as well as their included side. So therefore, triangle DAB is congruent to triangle BCD because of ASA. We ran out of room beneath the formal proof there, but that's the next stage as long as the reason. And now that we have two congruent triangles, AB and DC are corresponding parts, so they are congruent by CPCTC. Corresponding parts of congruent triangles are, in fact, congruent. So now here's your chance. If you do not pause the video, write down the if-then statement, the diagram, or the proof. This is your chance to do it. Go ahead and do that now, or just hang out on the video here for a few seconds until you're ready to see the formal definition of the distance between two lines. And so now that we're here, the last slide on the video is just the distance between two parallel lines is the length of any perpendicular segment connecting the two lines. Because of what we just saw, that if two lines are parallel, then all points on one line are equidistant from the other line. That means that any perpendicular segment is going to be congruent, so we just have to find one and measure it. So go ahead, pause the video because the video is about to end and you're about to lose the screen. Copy down the definition of distance between two parallel lines as well as the diagram, and that is a wrap for this video.